So I just want to first announce that the next meetup is going to be on Wednesday. Some people didn't like Tuesday, so we'll move it around, I guess.
People didn't like Tuesday?
I don't know. It seems like,
Okay.
you know. But we're going to build a strip-based LED. So everyone loves strip LEDs, and we're going to put it on Ethernet. So we love Ethernet in this building, so it's going to be a fun project. So there's specific interfaces that Ethernet uses. So today we're going to talk about IR LEDs. And most of this stuff is just squiggling, turning on and off a pin or an LED at a different rate or a different pattern. And we're going to learn about how to do it on Ethernet, which is called MII, or Media Independent Interface. And then also MDI, that's how you set up the actual physical layer and then actually physical layer. So someone actually went ahead and set up an Ethernet interface using the PIO peripheral. It's really kind of fascinating. So we're going to use that guy. We might use their code, maybe not. But then also strip LEDs, which I feel like the PIO was invented to control strip LEDs, just because they're such a pain in the butt with every other device. We'll talk about different ways to do that next time. I don't know if we'll do a custom board. There's actually an Ethernet board available that I might be able to buy from China for $2, so I'm going to try to use that before the meetup. We might do a small board for strip LEDs, just because usually they're 5 volts. You can get them in different voltages, but since you need to put some translators and stuff, and since driving strip LEDs is super fun, and you can think of probably 1,000 projects you can use it for. It'd be cool to have a little board that makes it easy to use, makes it easy to do. So
For next time already?
yeah.
Man.
So there's a lot of activity in this meetup chat. But basically, we're going to learn how to use infrared controllers. So anyone who has a TV has one. Some TVs now use Bluetooth and things, but almost all of them still support infrared communication, and there's kind of some standards around it. I picked Roku TV because that's what I use at home, just because they're super easy to use. And most people I know, there's more than one remote, they just kind of get confused. So when I would go on a trip, everyone would be like, we couldn't figure out the TV. So Roku kind of fixes that. It's kind of the pinnacle of user interface design as far as I'm concerned. So what we're going to do today is we're going to use the Raspberry Pi Pico to send and receive these IR messages that the TVs use or any other type of appliance that's infrared. So like I have an air conditioner that uses a infrared remote. So I'm hoping to use this with that to control.
I've got a. Okay, I don't have the TV, but I've got. Okay.
Yes. Does anyone else not have a TV? I'm just surprised. There's some great Netflix you can watch probably for years.
I'll be honest with you, when I first looked at my apartment for 3 months, I didn't see it.
Yeah. By choice?
Yeah.
Use your laptop though. Okay.
You got me.
Okay.
No, I've got the AC.
That's okay for a tech nerd. So some of you might have brought your own TV remote. I've tested this out on one other TV and it happened to work. So maybe you'll get lucky, or you'll have to do a debug session. But today you should get all the tools you need to debug it. So if you were here last time, we got the Pico board to flash an LED, and it's really hard to do because you have to get all the tools working. And so if you were here last time, there's probably 5 or 6 things you have to install properly and make sure the tools can find them, and then there's a lot of moving parts. So flashing LED is quite an accomplishment. So today we're basically going to flash an LED, but we're going to do it different. We're going to do it faster. So that's basically what this board is right here. Is there's an LED and it emits in the infrared spectrum range. So you normally can't see this unless you're either the Terminator or the Predator, right? Alien versus Predator, but they probably can see it. But anyway, there's an emitter here that we're going to control with the Pico. There's also a receiver as well. So there's a receiver IC So the way the project is set up right now is there's a hard-coded Roku code for OK, I think, or play, and then if you point a remote at it, it will learn the IR code that you sent. So ideally, you could go home, press power button on your, point it at this, and then you have a new power button. We have these solderless breadboards. So the quickest way you can build something that will fall apart very easily, it's not as bad as Legos, but is these solderless breadboards. And I put the links to these in the Meetup. And it's this right here. So you're actually going to plug your Pi into this, and then you're going to plug this board into it. It should just pop in very nicely. And then you're going to wire up the right pins. Now there's not that many pins you have to wire up, so there's only I think 3. Or there's 3 and then 2 power pins. And that should be all you need to do in terms of building your hardware. Now, the Pi you got last week does not have headers. It's just a board with holes in it. So you need to solder headers into the board to make it work with the breadboard. So maybe some of you are terrified of that, but we have a lot of people here, and we have headers, and we have 2 soldering stations. Yeah, and learning how to solder is a great thing. So
yeah, I've done it. I just wasn't that good at it. That's why.
Yeah, I mean, I'd say learn, and you can learn today if you want. So it's just
all right.
This is just to have fun doing stuff. Let me show you the schematic. Yeah, this software is called KiCAD, and it's an open source electronics design software, and it's actually pretty good. I think I looked at this 5 years ago, and I'm like, no. But now they did a great job. I feel like it evolved pretty nicely. It's free and it's easy. It's really easy to use. Surprisingly, well supported. This is the schematic. I did this in about 2 hours. I mean, this whole project I did in like 2 or 3 hours. So, and I just ordered it from China and it was here a week later, during COVID even. This is the pin header. So there's 6 pins on the board. There's 6 pins on the board itself, and there's a IRTX, and that's the pin that will be toggled by us to send the IR data. Now that connects. You can actually derive an LED directly with the Pico, but it's got limited current capability. So these LEDs, they can handle a decent amount of power and current, and that will affect your range. So instead of just driving the pin directly, we actually drive it through a transistor driver. So basically this is just an amplifier. So a small amount of current, this will generate 100 times the amount of current, basically. Basically this is a driver. We also run it at 5 volts to give it a little bit more power. Now, you might say, well, the Raspberry Pi Pico can't handle 5 volts. Well, the transistor kind of isolates it from that 5 volts, so the current path is just through this way, and there's no current that goes, or a small amount of current that goes this way, and then the voltage here is only diode drop. Now that's electronics. You don't need to know any of that because we're just going to toggle this pin, and the magic's just going to just happen. The other thing that we have a button, and basically it has 4 pins, and they're normally not connected. Okay, so there's 2 pins normally not connected, normally not connected. NO means normally open, and we only need 1 signal, so we run it from this side. That's the button input. So that button input is going into the Raspberry Pi Pico. Now, if you know anything about electronics, this doesn't really work normally, but the Pi Pico has resistors inside the chip that you can pull this pin up to logic 1 when it's not being pressed. So normally this pin will sit at 1, and then when you push the button, it goes down to ground because it completes the circuit through the normally open connection. Finally, there's this awesome chip here that decodes the IR. So what you're gonna learn is that we actually generate a square wave, a modulated square wave, which you'll see on the oscilloscope, and it's at 38 kilohertz, if I remember. But it's a very fast modulated signal, and it's amplitude modulated, so it's turned on and off. It's very common with wireless protocols. That's how radio works, is that you have a oscillator and then you do something to it, various frequency or amplitude. So anyway, that's kind of complicated, but this thing makes it real easy. It decodes that 38 kilohertz and just puts out the actual IR data. So it's a nice clean signal.
The IR is running over AM?
It's basically a 38 kilohertz. I guess I don't know if you call it amplitude modulation. It's probably post-close.
On-off keying or
PCM.
on-off modulation. I think it might be a better.
What?
On-off keying or on-off
Yeah,
modulation.
yeah.
Would be,
Yeah, I'm not an expert at the wireless terms, but yeah, you'll see it. And then on-off keying sounds, I mean, it is amplitude, but it's not exactly what, wire. Anyway, it's a real nice signal coming out of here, and then that will just go into an input on the lab. So, fairly simple circuit. It worked first time. First board I actually designed myself in probably I don't know how many years. It was fun to do. We actually at Trumpet we use something called Altium, which is a really high-end package, very expensive, but it's it's a lot to learn. And it's a lot to. This is actually really kind of comfortable. There's lots of support, lots of videos online. You download it for free, and if you're doing a home project, you don't need to get this huge piece of software to learn and do.
Question. So we created schematics up there.
Yeah.
How did you tell the supplier to put the holes here?
So this is the first part of any type of engineering or electronic engineering design. You start with a schematic which explains all the connections, what the components are, what the connections are, which is called a net list. After you do that, then you go to the board, and this is where you define all that. So what it does is it'll bring all the components. You pick the packages. I wish I didn't pick that. That was really hard to solder. That was a mistake. But anyway, it picks the packages, and then you just define the board outline, and then you place all the components, and then you connect all the wires. This particular board is a 2-layer board, which means there's traces on the top and there's traces on the bottom. So for a very simple board, you can do that. People that are very talented can do it on more complex boards, but normally they use multiple layers. It's more of a cost thing. So it's always good to have a whole layer of power and a whole layer of ground.
So did you I'm just curious, did you cut this board yourself?
Yeah, so what basically you do is you create these you create output files.
Yeah.
And there's all these board houses that do it. So I just use PCBWay, which is a Chinese one.
Oh.
Never used them before, and they have a page on their website that explains what to do with KiCAD to get what they want. And then you just upload a zip file with the design files. And literally it was a week later it showed up in my house. So, which I have more of the boards if you want to build any more. Build I got 100 of them, so. Yeah, so we'll talk more about that, but you can do things add a silk screen so all the writing on there, that's all added in the PCB area. Right, so it's actually this simple. So this is what the actually IR codes look, this is what the waveform looks like, and there's a header. What this means is that the IR, this green area is when the IR is generated. Now inside this IR is it's a 38 kilohertz on and off square wave. One of the reasons they modulate because there can be all kinds of light sources, and by creating a narrow filter around that frequency, they can filter all that out. So just like when you tune the knob of your FM radio to a different frequency, it's cutting all the other frequencies out. I don't know how they came up with 38 kilohertz. I'm sure it's online somewhere. But anyway, a lot of these protocols, it's all about there's bits and then there's widths, or there's a relationship to the previous bit. All these digital protocols, they're all like that. So this particular company here, we do like vehicle networking, and there's been like dozens of protocols, maybe hundreds of protocols over the past 20 years, and they're all something like this. They're like the bit's this long, it's this wide, or whatever. Anyway, this is IR. This is what we're working with. Basically, it generates this header, which is 9 milliseconds on, 4.5 milliseconds off, and then it'll actually generate the actual bits of the IR code, which is for the TV. So like every TV has different codes. I don't know how they figure it out, but online it looks like people sell databases. I guess it might be a business for that.
Hundreds.
Yeah. So anyway, there's it basically comes out to be a 32-bit number, and then it's actually only 16 bytes or 2 bytes, because the address, the first part is the 16 or the 8 bits. So the first part is actually inverted on the second part. So if this was 55, this would be AA. If this was 0, this is going to be FF. So you don't really have to know any of that. That's just how it is. And the same thing with the command area. So there's just really there's a 2-byte code, and we'll see in the software. Now this bit right here, depending on if it's a 1 or a 0, it's either going to be a small pulse followed by a short pulse, or a small pulse followed by a long pulse. So that's how they differentiate between 0 and 1. When we look at the code, you'll see that we just compare the time difference between the 2 pulses to determine if it's a 0 or 1. I don't remember the times, but I think it's like 600 microseconds and 1500 microseconds. But you'll see that this whole code is a fixed length and time. Now, even though the bits are in varying length, so zeros are shorter than ones, but the fact that you did the logical inverse means that 2 bytes that are inverse to each other take the same amount of time. It's kind of interesting. But you'll see that a lot of, when you look at on the scope, if you hold the button down, this actually will repeat multiple times. So if you're hitting the volume, it's going to keep going up. Now let's look at the code. There's actually a GitHub now for this, which is actually in the comments of the meetup. So you can actually you'll get this code when we sit down. We'll just get it. But what I'm going to do with this meetup is we're going to develop over time a class library in C++ to make all our projects easier. So you can think of it as like, Python has all these objects that you control things with. This is like exactly the same, but doesn't suck. It's actually fast. But no, I'm just kidding about that. Python has its uses, but if we're talking about it, we want to use C. And like you can use C++ in a way where it basically is C. So just going through the code, we include the library. So this is the class library that we created, and I'll show you what that is in a second. The project, the pin definitions. So a good practice is to put that in a separate file. And what's good about that is you can actually create different projects that use the same code, and all you do is change this part of the file when you change the pins.
I don't know. See, is that an include of other code?
So the way it works is with CMake is that basically your folder, your files in your folder contain the different files, and what happens is, so this is just a file in your directory, and then this is a header file, which is it's a file that has no code in it. Yeah, and it could have code in it, but it wouldn't be compiled. But anyway, this contains defines that say button board is equal to 16. So that what that is saying for this project is that's saying that we're connected to GP 16 right here. The button is connected to that pin. So if you decided to connect to a different spot, you can do that. All you gotta do is change this number. And then these are the other connections: GP 18, 17.
Right. Oh, I see.
And then forget about that. We're not even using that, so that's just a leftover. This is actually the LED on the board. That's always 25 on the Raspberry Pi Pico, which it actually shows it on here. It's very. One of the things that's nice about the Pico is that the pins are very flexible. So a lot of other microcontrollers have a ton of pins, but you can only do certain things on certain pins, which is like when you have like a 2,000-page data sheet, you always get caught when you design a board, like, oh, you can't do it on that pin, or that pin's analog, or like not, there's all kinds of gotchas, but that's pretty clean how they designed it. So it's just another reason why this part is a lot of fun. Here's some IR codes for some Roku button remotes. So these are just ones that I just learned with the sensor. And I'll show you how you can add to this.
That's 2 buttons. OK and play.
Yes. So
Okay.
this is the code that we send for OK and play. And I got these just by reverse engineering. I have the remote and I pointed at there.
Right. The RX.
Yes.
And it picked it up. Right. Okay.
I mean, if you were a true baller, you wouldn't need the RX sensor at all. But
If you're a true what?
baller,
Baller.
which those people exist.
How does that work? Just look at it and you can see the flashes?
Yeah.
Yeah. If you're from Krypton. You're from Krypton. So these are the class objects for instantiating. We're an LED, a button, and IR com. So what's nice about the class library, next time when we use an LED, it's already, all the code is just basically done. So it's not that complicated. Initialization. So have you heard of Arduino? Arduino is just C++, except they hide a lot of it. We're basically doing the same thing as Arduino, except we can actually use a debugger, which the newer Arduinos have it, but I've never used it. So basically, initialization, we initialize the LED, button, IR. We start out with the IR code, which is the play button, and then we'll enter in a loop. And this loop is very simple. It waits for the button to be pressed. And then it's going to build the IR data from the code, and then it's going to send the IR data in we call it a state machine. I'll explain what that is. But there's different ways to write your code. A lot of code designs are blocking, or like examples are blocking, which means that you have to finish this step before you move to the next step, which is incredibly limiting for any type of project that's complicated. So if you look at like a lot of the Python stuff you're thinking about, a lot of that just is like, I'm going to do this, and I'm going to do this until it's done. So these things, you saw that IR message took about 70 milliseconds. So that means you can't do anything that whole 70 milliseconds. So we're going to talk a little bit about that. And then we just toggle the LED, and then that's that. Then it continues on the loop. If the IR is not active, then it just continues to check for the button. If it is active, what it's going to do is It's just going to sit in a loop and read the IR data, and then it's going to process it. And then it's just going to wait till it's done, and then toggle the LED in a different pattern so you can see it. So, just an example, I have the board here, and I'm going to go ahead and you can see, I don't know if you can see the LED flash.
I can, yeah.
Could
It's flashing at the same rate as the IR is?
No.
No?
It's flashing at this rate.
So it's reading the
Okay.
it's reading IR data from the remote.
Yeah,
If you use any other remote, it will still flash as well.
that's right. Someone who brought another remote to see it.
That was your Roku as well.
And then apologize to your significant others since they can't watch TV tonight. It's a nice day though. Yeah, so you see this is going. Wait, this
Same rate.
is a Roku remote. Yeah, whatever.
But if you have like whatever
It
IR
doesn't work
remote,
on that TV though.
Yes. So I tried this on one other TV when I was on vacation last week, and it did work. So I'm curious. I would be love to hear if someone went home and. So we got some of these oscilloscopes for the Meetup to use, and these are really great. So what you want to do is install this software if you haven't already. But this is.
It works with the laptop to be an oscilloscope.
Yeah, so like this is an
Okay, that's
oscilloscope.
Well, that's why we put the Pico scope
Yes,
on.
yeah.
Got
So
it.
ideally what you'll do today is you're going to take this, you're going to connect to the IR input and look at it. And same thing with the output.
Okay.
So I did this with my Pico scope. I have a bigger one. Although I like this size better for going places. So I've connected it to the IR input, and I have my Roku remote, and I'm going to go ahead. The trick with this, first of all, an oscilloscope, if you don't know what that is, all it is a plotter, and it's a plotter of voltage versus time. So since we're toggling pins, turning them on and off, we can kind of see when those pins are being toggled on and off.
are those all milliseconds in the bottom? Or I forget what the X, Y axis.
Yeah, so what's weird about an oscilloscope, which I think is stupid, is that this is a carryover from the original CRTs that they always have in like sci-fi movies, and they show the little,
Well, when
but-
some of us went to school.
Yeah, but I agree. I prefer like using it as like a DAC, data acquisition equipment where it's just time, Y versus T, Anyway, the oscilloscope has a grid, and then you set the grid timing with milliseconds per division. So one grid is 20 milliseconds. And what's cool?
One rectangle?
Can you see this dotted line?
I see the rectangles, yeah.
Yeah. So that's the graticule, or what do they call it?
Yeah.
Okay. So basically, one horizontal block is 20 milliseconds.
All right.
Okay. So another thing, what's awesome is the oscilloscope has cursors. So does anyone remember the amount of time that start pulse was?
30,
What?
38.
It was I forgot what they said, but it wasn't 9 milliseconds. It was close to 9. Does anyone else know anything weird about this waveform compared to the one I showed you, the graphic?
Isn't it upside down?
It's upside down. Yeah. So that's something you'll run into a lot in embedded systems. So it's not like 1 or 0 don't necessarily mean on or off. It's like, what is the active state? So in this particular scenario with this sensor, the active state is low. So it's inverted. Now, to actually capture this waveform, you have to use a trigger. And since it's a waveform that happens not all the time, you have to set it up either in single or repeat mode. Now, for a lot of protocols, the Picoscope will actually decode the protocol for you, which is pretty cool. I did not look and see if they did that for IR, but there's a lot of protocols like I2C, SPI, CAN. This software actually does it.
Is that scope like faster than a regular oscope, or is it like a logic analyzer speed?
It's actually it is depending on which one you buy, it's equivalent or better. So Pico scope starts out with pretty low end, which this is actually close to low end. But we bought like the upper model just because we wanted to have some depth and memory, which is
It says 100
yeah 50 megahertz bandwidth. But like this is a low end scope for them, so they have 10 gigahertz scopes, for example. Not that you need it, but it's really way better. I mean, some people are knob people, I guess, but you know, if you have to go to the factory or a plant, you know, this is way better. Or you go home. You're working from home. You're gonna bring your $30,000 scope home. I don't know. Anyway, so that's what that looks like. And then if you connect to the transmit line, all right. So the difference between the receive signal and the transmit signal.
Oh, this is what's coming. This is what's coming in from the photodiode,
Yeah, this is the output.
and what you're seeing there is probably that's the 120 hertz flicker from the lights.
Well, this might be, but like, what? Why is this? Why is this like? Why does it look like that up and down? Does anyone have any idea?
Going from inactive to active.
Well, what happens is when we're centering that code, the time between the on and off, this is actually 38 kilohertz. So this is the modulation.
Modulation to
So I'm going to go ahead and increase the speed of the scope. So can anybody tell me what the period is for a 38 kilohertz? All right, so 26.65, is that right?
Yes.
Great.
Yep.
All right, so you kind of get the idea of the signals we're working with. Now let's look more in depth at the code. So let's look at the receive code first, or we can look at the class library a little bit. So the most basic of basic is the GPIO. And so you'll see a lot of these C calls in their GPIO underscore. So Raspberry Pi, part of their support is they have a huge library of C functions. And, a library is cool, but like one of the problems with libraries is that it's kind of another layer of abstraction over the datasheet. So you actually have to learn two things in. So I don't know how I feel about them, but at this point, you're very useful to me. And also, the libraries, when you install the SDK, the source code for the libraries is included. So you can actually learn a lot about the part that way. So since we're just having fun, we can use their library, completely understand it. But anyway, so this is our init function, and there's things you could do with GPIOs. You can make, the most common thing is it input or an output? Yeah, I mean, it's never sunny in Michigan. What the hell? This is why so much gets done in Michigan. No one wants to go outside.
Except for today.
So today, our Shanghai office, no one is allowed to leave their house for any reason. Except there's one reason they can, and that's to walk their dog. So
why can't it go?
because they're on zero COVID lockdown.
Oh,
So they're not even allowed to go get food, or I don't know what they would do outside, but
So they can walk your dog.
they can walk their dog. So having a dog is a great thing in China. So everyone knows that dogs made out during COVID. All right, what can you do with the GPIO? You can make it an input or output. And then, as I mentioned before, this part has internal pull-up and pull-down resistors you can turn on. So the concept of the class is all this code, you kind of create an API that's simpler. And your API it might hide a lot of the ability of the part, but it only should if it shows just what you use, it kind of saves you time in the future. So, is this like the best class library you can design? Maybe it is for the meetup, but maybe it isn't for you at work. But it is a way to hide complexity. So the LED, here we have the LED. So what an LED is, it's really a GPIO that you know stuff about. So what do you know? It's an output. You want to drive it pretty strong, and it's got some basic API like on-off toggle. That's straight from Python. Just copy that. And then button, similarly, button has an active state, can be high or low. And then it's just calling the APIs. This one actually uses the GPIO class, which is the proper way to do it. Now, if you do a GPIO class really well, you could port it to other microcontrollers. So when Raspberry Pi, they're obviously going to come out with another chip at some point. It should be fairly easy to get working. But anyway, let's look at the big ugly code. So the first step is read IR data. All right, so here's our read IR data. So this is called when the IR receive line goes low. So it's that first start bit. That's that first 8 or 9 millisecond bit. So it gets called, and then it goes into a loop. So this is going to loop to IR measurement max, which happens to be 120. For no reason, it was just me hacking. It calls an API call that's called get absolute time, which actually returns a 64-bit number. One of the cool things in the Pico is they actually have a timer that's 64-bit, which is like, finally someone did that. Because the beauty of a 64-bit number is it will never overflow.
Well, it will, but you just have to wait much longer.
Yes.
I'll be dead.
Yes. It's like a year 20. It's like a year 2000 problem. You know, but it's year 20,000. So if your code is around that, I feel bad for the world. So what it does is it just sits in a loop and it's waiting for the pin to basically change. So it starts out with looking for a 0. It measures the time when it actually changes, and then it calculates the difference. And it has this one limit. If it's longer than 10 milliseconds, it just stops because that's an invalid code. So if not, then it just continues into the bottom here. It records the time into this array, and then it toggles the next bit. So this is the bit we're looking for. So then it just sits there and gets the time again, waits for that bit to happen, and then records the time into this array. So it just does that in a loop until it's done. So until the time goes too high. Anyway, so after we have read IR data, we recorded all basically the time deltas between all the edges of that message. We go into here and we call process IR data. It's gonna iterate through that array. So it starts out, it says make sure there's at least 16 recordings of the bit. We kept track of how many bits we got. The first 2 bits, in order for it to be valid, it has to be between 7 and 9.5 milliseconds. I just picked those arbitrarily. And then for the second bit, it's got to be, the spec says 4,000, so I just say 3,500 to 5,000. And if it passes that test, then it goes into the bit time calculation. So now what it does is it looks at the next bit, and if it's between, if it's not between 400 and 650 microseconds, that's invalid. Because it always expects a short pulse to start the bit. And then the differentiator between a 1 and a 0 is the length of the second bit. So the second measurement here is the second bit long? That means it's a 1. And if it is, I shift that into the IR code. And so for every bit, it'll just be shifting into that IR code bit. Once it hits 32,
Shifting 1?
well, basically what this does is, so this is it's like an exponent of power of 2. So it starts out at 0. So if you shift 1 over
okay.
0,
Oh,
it's 1.
okay.
And then
Right, okay.
if it's 1, it's going to shift it over 2. All right, so once it hits 32, it's done. Okay, so now we have this IR code that we captured. And then the next thing we're going to do is the receive is done. Well, we just wait for a button to be pressed, and then we build the IR data from code. So we'll go to that back there. So it kind of just does the same thing in reverse. Takes the code, goes through the 32 bits. It builds the IR bit times. So the first one's the start bits. And then it goes through, if it's a 1, it's going to be a short pulse followed by a long pulse. If it's a 0, it's going to be 2 short pulses. Then after that, it's going to send data through a state machine. Now, there's also this send IR data, which basically just sends it and doesn't return until it's done. But this send IR data from state machine will actually start sending it, but it will let your code continue. As long as you call that function periodically, it will automatically do what it has to do to send the waveform. Which I don't think I'm going to talk about this, but you can look at it. So we'll just look at the send IR data. Which I renamed to blocking. So this is a loop. So we go through each bit, and then we turn on the PWM. So there's a PWM enable. Now what the PWM is the peripheral in the Pi Pico that just will generate a square wave with a specific duty cycle. And that's how we generate the 38 kilohertz. So the first thing we're going to do is turn it on, and then we get the time, and then we basically wait until we get to that, whatever time is in the array, and then we just turn the PWM off. So we're basically toggling the PWM on and off. So let's just look at the PWM enable. Let me show you the initialization. So most of there's 16 possible PWM outputs that you can generate with a PWM peripheral. So they almost work on every pin. And then if you wanted more PWM, there's like 10 different ways to do it with the part. But anyway, using the PWM peripheral, it uses a GPIO. So you can set a function on the pin to be a PWM. So not every pin can do that. But I think maybe the sheet shows you. No, it doesn't. Wait, yeah, it does. It says GPI, PIO, PVM. So anything green, basically. Then this is just the API call. So if you looked into the examples in the Pico SDK, it just shows you how to do it. Shows you an example. But I had to figure out what the period is going to be for 38 kilohertz. I don't know why I have 48 kilohertz here, but that's probably why it didn't work at first. So there's two numbers for PWM. One is going to be the frequency or the period. The other one's going to be the time on, which is the duty cycle. So since we don't care about duty cycle, it says 50%. So this number basically is the default clock rate. If you don't underclock or overclock, the Pi Pico clock rate is 125 megahertz, which is real confusing because they always talk about how it's 133 megahertz apart and like different areas, but it's I can tell you it's 125 megahertz, and the 1 over 125 megahertz is 8 nanoseconds. So each system clock is 8 nanoseconds. So if you wanted to find out what 38 kilohertz is, you figure out what is the time of 38 kilohertz, the period, 1 over 38 kilohertz, which someone said it was 26 microseconds. So you divide that by 8 nanoseconds. So going backwards, I have 3289. So 3289 times 8. So that's 26,000 nanoseconds, or 26 microseconds. And then the level, or the duty cycle, is half that, so it's 16. All right, so that's the setup. So once the PWM is set up, then you just turn it on. So you generate that square wave whenever it's on. So coming back to the enable, it's as simple as telling the GPIO you're going to use PWM, and then you turn it on. The disables, there's one extra step, which is turn off the GPIO pin. Because I wasn't sure when you disabled the PWM, was it going to be left in the state?
It'll be left in whatever state.
Yes, yeah, I was worried about that.
You have to basically revert, if you want to have control of it and put it into a known state, you have to take control of the pin from the PWM and make it a GPIO and set it whatever state you want.
Yes, yeah. So step 1 here, turn off PWM. Step 2, just disconnect the GPIO from the PWM and then reconnect it to an output pin. And then step 3, make the output pin 0. One small thing I learned about the PWM, which I don't understand yet, but I got it working. One of those things, and Meetup was today. There's something called a slice for the PWM. And I don't know why the API just doesn't figure this out automatically. I just don't know.
Because they didn't, the SDK, if you look at the data sheet on the card on the RP2040, I mean, this is like you look at the SDK, these functions are very thin wrappers that go right to the control registers. And so if you look at the internal structure, there's like 8 of these PWM engines, and that's why they call it a slice. And each one of them has its own counter, and they all have their own top value that you can set to set the maximum. Maximum to set the period. But you've got individual compare registers, and then each one of those goes to one of the 2 GPIO pins associated with the slice. So the bottom line is they just a better abstraction library would have given those details from them.
Yeah, I guess my point. I mean, basically, you're absolutely right. There's only 8 PWM peripherals, but each one can control 2 outputs, and each 8 have to share a frequency, but they can have different duty cycles.
Yes.
But each GPIO either belongs to the channel A or B of each PWM. So that's the trick, is that if you change the pin number you're generating the PWM on, you have to make sure you're on the right channel, A or B. So, is there an API that just tells you that? I hope so. I didn't look for
I
it.
think there is one.
Yeah, because they have this GPIO to slice number, so you think they would have GPIO to channel number.
Yes, they do.
Okay, so this
I'm
code
pretty
could be
sure
better.
I just used it.
So it's great to bring this up. So let's look at the actual code for these functions. So let me pull it up. If you install the SDK, which is what we did last time, it's going to have this directory called SDK, and in it there's source, and the source code for all those APIs are going to be here. So, all right. So this right here will show all the directories, different libraries. So I'm going to go into PWM. All right. I guess they have this is all inline code. So basically, this is the source code for interacting with the PWM. Now, if you read the data sheet, and you're a purist, you just read the data sheet. With the library, ideally makes it easier for you, and it also is documented. But you're left at a position where the data sheet is the ultimate authority on what the part does, and then depending on who wrote the library, it could be good or not good. It could have been an intern. Not that interns don't do good things. It's just that they're just not around long. Or I guess the good ones you hire, but anyway, back to this. What's nice about the SDK is that all the code's there, and you can actually, if you were a purist and you're going to read and write registers directly from the data sheet, at least there's an example of someone doing it. So there are some questions you might have that isn't really obvious from the API documentation. Like how interrupts work. Like it wasn't clear whether interrupt. We're not going to talk about interrupts today, but like, do you clear them or not clear them if you use the library? It wasn't clear. I don't see it documented anywhere yet. But that's just an example where using a library can lead you to more problems than just reading the data sheet. All right, I think that's all for me talking. So now the goal is for you guys to get this code working. And I can do the Netflix button.
Okay.
Use the actual remote control on the TV and make sure that works first.
Yeah, it works. So.
It's powered.
I think the button's working. It's just for some reason the Roku is not connected to the internet.
It's not. It shouldn't have to be though. Yeah, I hit the Netflix button. Like it. Anyway.
Wait, since it has one button, you can get it to do one thing.
Yes. But I mean, you could add more buttons. This is only a starter for you.
Right. Okay.
It depends on what you want to do. So, like at my house, I have like a surround system in my basement for the theater, but it's in a closet, and I don't want to have to use the remote from the sound system to change the volume. So I'm going to use this board to use the Roku, like the volume on the Roku, and so it's going to receive this and then send out the right volume for that.
You would
remote.
need two buttons, one for volume up and one for volume down.
I'm just going to use this remote to control the home audio system.
Okay.
So basically repurposing these buttons.
Okay.